All right, let's dive into one of the coolest systems in our bodies, the circulatory system. It's like biology 101, but way more exciting.
Definitely more exciting.
We're going to break down how this system keeps your blood flowing, even against gravity.
It's really an amazing feat of biology.
We've got excerpts from a biology textbook as our guide today, so think of this as a crash course in all things circulation. Ever wonder how your blood travels over 100,000 kilometers of blood vessels?
It is a pretty crazy thought, isn't it?
We're going to find out.
Sounds good. And, just like a detective story, we're going to start by looking back in time. How did people used to understand blood flow before all the fancy technology we have today?
So, rewind the clock. What were some of those old school theories?
Okay, so imagine this. People used to think the heart was the center of intelligence, not just a pump.
Whoa, really? The heart is the brain.
Yeah, the ancient Greeks thought that. Then there was this guy, Galen, a Greek physician in the 2nd century. He had this idea about tidal blood flow.
Tidal blood flow. Like the ocean tides.
Exactly. He thought blood just ebbed and flowed throughout the body, like the ocean. He also thought that the arteries and veins were mostly separate systems.
So completely different from how we know it works now.
Yeah.
When did things start to change?
The big shift happened in the 17th century with William Harvey. He was an English physician. Harvey proved that blood actually circulates in a closed loop, pumped by the heart.
Hold on. How did he even prove that back then?
Well, he was a brilliant experimenter, and he used this simple analogy, the water cycle.
Makes sense.
Just like water evaporates, forms clouds, rains down, and flows back to the sea, blood does the same thing in the body, driven by the heart.
That's a great way to picture it. But you said there were some problems with that comparison, right?
You're right. Blood doesn't evaporate like water. His analogy, while amazing for the time, couldn't explain everything about how blood moves.
So there was still something missing.
Right. It wasn't until 1661 with Marcello Malpighi.
Okay.
He used the newly invented microscope
Ooh, fancy.
to discover capillaries.
Ah, the microscope. Game changer. So what are capillaries exactly, and how did they complete the picture?
Well, think of capillaries as these tiny blood vessels, so small that red blood cells can only squeeze through them in single file. They're everywhere in your body, reaching almost every cell. That's where the magic happens, the exchange of oxygen and nutrients.
So Harvey figured out the loop, and LP discovered the tiny connections that made it all make sense. Incredible.
Yeah, pretty amazing.
Okay, so we've got the blood flowing through this network of arteries, veins, and capillaries. But what about the blood itself?
Ah, yes. Blood is more than just a simple liquid. It's actually considered a type of connective tissue.
Wait, blood is a tissue? I never thought of it that way.
It is, and it has two main components, plasma and formed elements.
Wow.
Imagine plasma as the river carrying everything in your blood, mostly water, but also proteins, sugars, vitamins, minerals. The formed elements, like the vehicles traveling on this highway, the most abundant are the red blood cells.
Red blood cells. They're the ones that carry oxygen, right? How do they manage to carry so much of it?
Well, that's where hemoglobin comes in. Each red blood cell is packed with about 280 million molecules of hemoglobin.
Whoa, 280 million. Hemoglobin, what's that?
It's this protein that contains iron.
Okay.
It picks up oxygen in the lungs and delivers it to all the cells that need it. The iron in hemoglobin is actually what gives blood that red color.
So it's like a little delivery system for oxygen. But does hemoglobin just grab oxygen in the lungs and drop it off wherever?
It's more complex than that. Hemoglobin's ability to bind and release oxygen depends on a few things. One key factor is the concentration of oxygen in the surrounding environment.
Right, that makes sense.
In the lungs, where there's lots of oxygen, hemoglobin binds to it. But in tissues where oxygen is low, hemoglobin releases it.
So it's smart. It responds to what the body needs.
Exactly. We actually have a visual way to represent this, the dissociation curve. It's basically a graph that shows how much oxygen is bound to hemoglobin at different oxygen levels in the blood.
A graph. I love graphs. Would love to see that.
We'll definitely put a diagram of that in the show notes. Now, those incredible red blood cells are just one type of formed element. We've also got white blood cells.
Oh yeah, the infection fighters.
You got it. White blood cells are the body's defense force. Think of them as an army patrolling your bloodstream and protecting you from bacteria and viruses.
Awesome image. Are all white blood cells the same, though?
Not at all. There are a bunch of different types, each with their own special skills. For example, we have macrophages.
Macrophages, what do those do?
Macrophages are like frontline soldiers. They engulf and digest pathogens directly.
So they're like Pac-Man, gobbling up the ghosts.
Exactly. Then we have lymphocytes. They're more like the specialized units.
So if macrophages are the frontline soldiers, what makes lymphocytes so special?
Lymphocytes are all about targeted attacks. They make antibodies. Those are Y-shaped proteins that recognize and attach to specific things on pathogens called antigens.
So each antibody is designed to take down a specific enemy. Pretty cool.
Yeah. This binding either neutralizes the threat or flags it for destruction by other immune cells. It's like putting a target on the bad guys for the rest of the immune system to see.
Wow. Okay, so macrophages eat invaders, and lymphocytes launch targeted attacks. That's an amazing defense. Are there any other players on the immune system team?
Yes. We can't forget about platelets.
Right, platelets. They're the ones that stop the bleeding when we get a cut, right?
Exactly. And while they're not actually cells, they are crucial for blood clotting.
If they aren't cells, then what are they?
They're tiny cell fragments from the bone marrow. When you injure a blood vessel, it triggers a chain reaction, and these platelets rush to the scene.
Okay, so what happens when they get there?
They release chemicals that attract more platelets to the site and start to build a plug to seal the leak. Eventually, this leads to the formation of fibrin, a protein that forms a mesh to trap blood cells and solidify the clot.
So they quickly patch up the damage.
Exactly. And all of this is happening within the plasma, that liquid portion of the blood.
Okay, so it's not just the cells that are important. The plasma plays a vital role, too.
Absolutely. It's the transport medium for all the cells, nutrients, hormones, and waste products. And it helps maintain blood volume and pressure. You could say it's the lifeline of the circulatory system.
It sounds like everything in blood works together in this amazing, intricate system.
It really does. But there's one more layer of complexity we need to talk about.
Ooh, what's that?
Blood groups.
Ah, right, like A, B, and O. I know they're important for transfusions, but I've never fully understood how they work.
It can be a little confusing, but it comes down to the presence or absence of certain protein markers on the surface of red blood cells. We call these markers antigens.
So if you have type A blood, you have A antigens and so on.
Exactly. And our immune system is always on the lookout for things that don't belong. If you get a transfusion with the wrong blood type, your immune system will attack those different antigens.
That's why matching blood types is so important. What about that Rh factor I've heard about? Is that part of the blood group system too?
It is. The Rh factor is another protein marker on red blood cells. You either have it Rh positive or you don't Rh negative. It's important for transfusions, and it can also be a factor in pregnancy, especially if an Rh negative mother is carrying an Rh positive baby.
Wow, I see how that could be a problem.
Luckily, modern medicine has ways to manage those situations. But we've laid a good foundation for understanding the circulatory system today. We've explored blood vessels, delved into the world of blood itself, and even touched on the importance of blood types.
We have covered a lot.
And next time, we're moving on to the heart.
Looking forward to it. This system is just incredible. The way all those components work together is amazing.
I agree.
Welcome back. Last time we explored this amazing world of blood vessels and blood itself.
It's pretty fascinating stuff.
Now we got to turn our attention to the engine that drives this whole system.
The heart?
Yeah, the heart. Beyond its symbolic meaning, it's truly a marvel of biology.
Oh, absolutely. It's essentially a muscular pump, tirelessly working to propel blood throughout your entire circulatory system, and it never gets a break.
That's a tough job. So what does this biological pump look like? Like, if we could see it.
Imagine your fist. That's about the size of your heart. It's nestled slightly to the left in your chest, and it's made mostly of cardiac muscle tissue. It has this unique ability to contract rhythmically without getting tired.
Wow. Our skeletal muscles would be so sore if they had to work like that.
I know, right? And inside the heart, we have 4 chambers.
4 chambers, okay.
2 upper chambers called atria, and 2 lower chambers called ventricles.
2 atria and 2 ventricles. What do those chambers actually do?
Think of the atria as the receiving rooms. They receive blood returning from the body and lungs, and then the ventricles are the powerful pumps. They propel the blood out of the heart.
So, collect and pump. Sounds efficient.
It is.
But where does the blood go after it leaves the ventricles?
Well, that depends. It depends which ventricle we're talking about.
Okay, so tell me about both.
The right ventricle pumps deoxygenated blood to the lungs through the pulmonary artery. Remember that pulmonary circulation loop.
Yeah, the round trip to the lungs to pick up oxygen.
Exactly. That's where it gets a fresh supply of oxygen.
Yeah.
And then the left ventricle, that's the real powerhouse.
Okay.
It pumps the oxygen-rich blood out to the rest of the body through the aorta, the largest artery in your body.
So the aorta is like the main highway for oxygenated blood.
You got it, delivering it to every single cell.
So two separate loops, both powered by the heart, one for the lungs, one for the body. How does the blood know which way to go? What keeps it from going backward?
Great question. The heart has this brilliant system of valves. They're like one-way doors
Okay.
between the chambers and at the exits of the ventricles. These valves open and close with each heartbeat, making sure the blood flows in the right direction.
Valves. That makes a lot of sense. But how does the heart know when to beat? Do we have to tell it to?
This is one of the coolest things about the heart. It has its own internal pacemaker. It's a group of specialized cells that generate electrical signals.
Wait, so our heartbeat is controlled by electricity?
It is. This electrical activity spreads through the heart muscle, prompting each section to contract in perfect synchrony. That creates the pumping action.
Whoa, it's like an orchestra.
It really is.
But our heart rate isn't always the same, right?
Yeah.
Like when we exercise or get scared, it beats faster.
You're absolutely right. The heart's pacemaker sets the basic rhythm, but your nervous system and hormones can influence it, speeding it up or slowing it down depending on what your body needs.
So it's like a conversation between the heart's internal pacemaker and these signals from the nervous system. Fascinating.
It is. And speaking of signals, where do you think blood pressure fits into all of this?
Oh yeah, blood pressure. It's a big deal, right? Like how healthy your heart is.
It is. It's a crucial indicator of how healthy your circulatory system is. Basically, blood pressure is the force of the blood pushing against the walls of your arteries. It's highest when your heart contracts, pumping blood out, and lowest when your heart relaxes between beats.
Right, that's why we get two numbers when we check our blood pressure, right?
You got it. The top number, called systolic pressure, that's the pressure when your heart contracts. The bottom number, diastolic pressure, is when the heart relaxes. It's like measuring the peaks and valleys of the pressure waves.
Okay, so it's important to keep those numbers in a healthy range.
You got it. High blood pressure puts a lot of stress on your heart and blood vessels, and that can lead to problems down the road, like heart disease or stroke.
Okay, so what affects blood pressure? Is it just about how hard the heart is pumping?
There's more to it. Several factors contribute. How much blood you have, how elastic your arteries are, how much resistance there is to blood flow in your smaller blood vessels.
I see, so it's a balancing act.
Right. Too much resistance, and your heart has to work harder. And the elasticity of the arteries, that plays a role too.
So as we get older and our arteries stiffen, that can make our blood pressure go up.
You got it. Think of it like a garden hose. An old, stiff hose is harder to push water through than a new, flexible one.
That makes sense. So it's not all about our genes. We can actually do things to keep our hearts healthy.
Absolutely. Lifestyle choices like diet, exercise, and managing stress, they can all have a big impact.
That's good to know. It's great that we have some control over our health. This is also fascinating.
It is. And knowing how it all works is the first step in making good choices.
Well said. We've covered so much. The structure of the heart, blood pressure, what affects it. What an amazing journey.
It's a testament to the incredible design of our bodies.
Welcome back to our deep dive into the circulatory system. It's been quite a journey so far.
It has.
We've explored blood vessels, we've delved into the fascinating world of blood itself, and even taken a close look at the heart.
The engine that keeps it all running.
Exactly. So now it's time to bring it all together.
Sounds good.
Let's rewind and recap what we've learned. We started by going way back in time, looking at those early theories about how blood flows through the body. Some of those are pretty wild, right?
Oh yeah, like the ancient Greeks believing that the heart was the seat of intelligence, or Galen's idea of tidal blood flow.
Right, like the ocean. Blood just sloshing back and forth.
It's
It's incredible how much our understanding has changed.
It really is. And it shows how science works, constantly questioning and refining our knowledge.
Absolutely. Then, of course, we talked about William Harvey,
In the 17th century.
who revolutionized everything.
Yeah.
He proved that blood circulates in a closed loop pumped by the heart. And his analogy to the water cycle.
Brilliant.
So simple, but it really helps you visualize how the blood moves continuously through the body. And then later, Marcello Malpighi, using that brand new microscope, discovered capillaries.
Those tiny blood vessels connecting the arteries and veins.
Completing the picture. And speaking of microscopic, I was totally blown away by the fact that blood is actually a tissue not just a liquid,
A complex connective tissue.
with all these specialized cells, each with its own important job to do.
Like those red blood cells, packed with hemoglobin. Those little molecular taxis delivering oxygen all over the body.
And then the white blood cells,
The immune system warriors.
protecting us from those harmful invaders.
Right. And don't forget about the platelets. Those tiny first responders rushing to patch up any damage and stop us from bleeding.
It's like a well-coordinated team constantly working to keep us alive and well.
Working 24/7. And all of this is happening within the plasma, the liquid portion of the blood.
The transport system for all the cells and nutrients and everything else, it's really the lifeline of the circulatory system.
It is. And then, of course, we talked about the heart, the amazing pump that drives the whole system. It's incredible to think that it never stops beating.
Our whole lives.
And remember, it's not just one pump. It's actually two pumps working together. One sending blood to the lungs for oxygen, and the other sending that oxygen-rich blood to the rest of the body.
Like a perfectly synchronized two-sided engine.
Exactly. And we also talked about the importance of keeping our blood pressure in check,
Right. High blood pressure can really strain the heart and blood vessels,
increasing the risk of problems down the line.
like that stiff garden hose. Too much pressure, and eventually something's got to give. But the good news is that we have some control over our blood pressure.
Absolutely.
Lifestyle choices like diet, exercise, managing stress, all those things can make a difference.
They really can. Knowing how your body works is the first step to taking good care of it.
So true. This deep dive has been an incredible learning experience. I'm amazed by how complex the circulatory system is, but also how beautifully it all works together.
It's a testament to the power of nature's design. And as we wrap up this deep dive, I want to leave you with one final thought. Knowing what you now know about the circulatory system, how might you approach your own health differently? Something to think about as you continue to explore the fascinating world of science.
I love that. Keep those brains engaged and those hearts healthy. Thanks for joining us on the deep dive. Until next time, stay curious.